So hi everyone, my name is Felix. I'm a final year PhD student at CSAL, MIT. I work on Inference-Time policy customization, and today I'm going to tell you a little bit about how I approach this problem and what are the cool things I find along the way. So in 1968, Marvin Minsky built this technical arm at MIT. Essentially, they want to showcase the capability of building robot arms that can lift heavy objects, and also an arm that is controllable by user to do relatively flexible motion. So what's cool here is he built this tiny miniature version of the technical arm. So he's manipulating this arm, the smaller arm, and then transferring the motion over to the bigger arm to do manipulation tasks. And then fast forward about 6 years later, we have similar systems, such as this puppeteering Aloha system, where users are controlling one set of the arms to generate manipulation data, and then those data being logged to train super dexterous manipulation skills, such as the ones you're seeing here of tying shoelaces. So these capabilities were never was not there before, and then through 60 years of hard work, now we're at a stage where we can do super cool demos like this. So what we see here is we get better and better autonomous behavior generations throughout the years. We build better and better policies. The kind of question I'm interested in is there a way for humans or end users to actually steer the autonomous behavior generation towards their own use cases so that we can have better and better human-robot interaction experiences when we deploy these autonomous behavioral robots, behavior generation systems. And an example of a steerable system is Google Maps. Imagine you want to navigate your location. So you input your destination to the Google Map, and then the Google Map is able to give you multiple routes for the user to choose from. And the user just needs to click on a route and then modify the routes by dragging a clicking point around. And the Google Map will just reroute to accommodate the user preferences. Additionally, you can also customize the tasks you want to solve. For example, you can change your destination, and then the Google Planner will replan to generate routes that reach a new destination. So we see capabilities of both customization of the tasks you want the agent to perform, as well as the motions you want the agent to help you with. So to summarize this experience, this Google Map, this intelligent agent in this case, knows not only to solve different tasks, but also different ways of solving a particular task. And then the user interaction is essentially choosing which task you want the robot or AI system to help you solve, and also how you want the robot to help you solve it. And this process is very nice for the user because it requires very low user effort. The user just needs to click a point and drag around things, for example. And then the changes are instant. That is, you don't need a robot to update its own knowledge base to generate motions. And lastly, all of the executions are feasible, meaning they're collision-free, they're drivable routes in a real environment. So that's very nice. And the reason these executions are feasible because it comes from a planner, right? Because the Google Maps plans in real time. So what about manipulation policies that are pre-trained? Can we also achieve, feasible executions after interaction? That is, can we be able to somehow get the motions from this valid motion manifold, which is defined as a set of feasible executions, possible executions? If we can ensure all of the motion generation live on this motion manifold or is sampled from the set, then we can achieve similar behaviors, interaction experience for human-robot interaction. So let's look at how our pre-trained policy currently work out of the box. If you pre-train some policy, let's say in this case, a diffusion policy of picking up one of the different objects, and then you deploy it in a new environment, you give it an instruction, ask you to move the yellow coin to the plate, and you execute the policy, 0 shots. Sometimes you will find this kind of behavior. That is, the robot is able to do something successfully, but just not the thing that's intended by the user. So, for example, in this case, it picks up the wrong object. So what we see here is a lot of the pre-trained policy by its own, even without human interaction, other than the pre-trained language instruction, it lacks robustness. That is, they don't always perform the task we wanted to perform. Additionally, when the policy is making mistakes, there are no easy ways for the humans to quickly adjust or steer the policy so that you can actually correct the mistakes online. Typically, what people do is they will try the system again, use a different prompt, for example, and hopefully it will work. Another way of fixing this issue is you can just ask the user to collect some additional data, and then you fine-tune your policy with that additional data for that particular task, right? This is one way to increase the robustness. But additionally, you could also fine-tune your policy to now input online interaction or correction inputs. So now you can also somehow change the policy weights or structure so that now it accepts this online correction to improve stability. I call all these kind of changes training time adaptation because it requires changing the weights in your model. This is very well and this is all very effective and good approaches. But imagine you're the end user who actually needs the help right away, right? You're busy with your task in a factory floor, on the factory floor, and then you need a robot to help you fetch some tools, or you're busy preparing your breakfast, you want the robot to help you right now, or you may be someone with disability and you really want the robot to help you with your task. In all these cases of using robot, the human, the end user, may not have the capability or the infrastructure to do data collection or fine-tuning, or maybe they have, but they just don't have the time to wait until fine-tuning to finish. So in all these cases, there are ways for us to somehow take a pre-trained policy that lacks steerability, but somehow make it steerable without changing the policy at all, and then now use our user interaction to improve the performance and align the robot behavior. So this is the kind of research question I investigate in my research is, can we do something called inference-time customization that doesn't require training, that can help the robot perform better through interaction with humans? So to explore this idea, I'm going to first talk about a framework called inference-time policy steering. That is, we assume the policy has learned good skills. It has captured a good motion manifold or distribution of skills, and then we want the users to be able to learn or indicate or steer the policy to generate one task or the other. For example, let's say you have learned a good policy of manipulating different objects in the kitchen environment. In this case, there's 3 skills. How can we allow the users to use pointing inputs or sketch input or physical nudges to choose one task or skill to perform over the other? The other case is when the pre-trained policy has not learned a really good skill set for a given environment. Let's say sometimes it makes a lot of mistakes. And then when the user wants to customize the behavior, especially the motions, let's say the user wants to prefer the robot to execute a task of reaching some marbles from a particular part of the state space. How do we ensure those interactions is not going to actually exacerbate the distribution shift and fail the task eventually? That is, how can we somehow improve the robustness of policy with imperfect skills? And in this cases, we allow users to use physical corrections or nudges to indicate motion preferences, while we allow users to monitor the process and then indicate when the robot is making a mistake so that the robot can recover from it. I call this framework task and motion imitation because we want to do imitation learning subject to task constraints. And then the last bit of the talk, I want to extend this framework and then relax the assumption that we require a user to monitor the process. Can we somehow learn a classifier that monitors when the robot is making mistakes? And if so, then we can actually just use that classifier to auto-detect mistakes and allow users to just focus on nudging or steering the policy without worrying about the monitoring process. So without further ado, I'm going to get into the first part and talk about how can we steer policies without introducing distribution shift. Inference-time policy steering. Here, given a non-interactive policy, in this case, for example, the robot is predicted to trying to pick up the left ball, and then a red sphere floating in the 3D space, a point cloud that indicates the user intent, right? The user is using a mouse to control this red sphere to indicate its goal. Can we somehow combine those two signals and then steer the robot to perform a different task, such as to pick up the right ball? Here, the red sphere turns green, indicating the steering is being activated. And when the steering is activated, we want to see a behavioral switch. So to understand the framework, first question is, what kind of non-interactive policy do you want to consider? What is the base policy? In this work, we investigate several policy class, but the one with the best performance is diffusion policy because it has a good structure to learn multimodal data distribution. So you can learn multiple skills very easily and effectively. And then the kind of user interaction we want to consider in this work is threefold. One is a point input. Let's say we have a user choose a pixel in the scene image and then map that to 3D space. This is a good way of indicating point goals. But when the user has continuous preferences, we allow users to generate a sketch, such as using a VR controller or draw the 3D trajectory on a sketch pad and then map that to 3D space. So this is a way to indicate continuous preferences. And lastly, we allow users to physically nudge the anti-factor to correct the behaviors in the action space of the robot. This is the last one. Last kind of interaction we experiment to tell the robot what the user intention is at inference time. Okay, given the different kinds of interaction input, how do we combine them individually? For example, with the non-interactive policy to bias the prediction. That is, what sampling procedure are we performing to steer the policy? Guided diffusion, that is diffusion with classifier guidance, is one way of achieving. We use this as a baseline. So the way that works is, let's say you set your diffusion policy, start from a Gaussian distribution, and then you gradually remove noise from this a noisy sample, and eventually you arrive at a clean trajectory. But because this process is uncontrolled right now, you might end up with skill 1 or skill 2. You don't have any control over this process. Let's say the user now wants to control this process, and then the preferences is indicated by this user sketch. We can code up some heuristic function, turning the sketch into some alignment gradient. For example, using L2 distance between the sketch and then the noisy trajectory, we can get the alignment gradient that will nudge the denoising process closer to the skill preferred by the user. And if you keep doing this, theoretically, you will be able to control the denoising process and arrive at the skill that intended by the user. And then the pseudocode of this guided diffusion is super simple. It's just within each denoising step, you are adding an alignment gradient on top of the denoising gradient to somehow nudge the process closer to user preferred direction. But if you try this, actually what you will see is whenever the steering is activated, this alignment gradient will actually introduce distribution shift and then cause the robot to generate incoherent behaviors. The reason that happens is every time the alignment gradient is added on top of the denoising gradient, you slightly bring the policy out of distribution. And when you have lots of diffusion steps, eventually you are completely out of distribution. So how can we bring the process actually back in distribution so that we don't allow the steering process completely derail the robot behavior? The simple fix we found working effectively is to, for each denoising step, you can actually add noise back so that you stay at the same noise level and then do this back and forth sampling times for multiple rounds before moving to the next denoising step. So from a pseudocode perspective, that just looks like within each denoising step, you're performing multiple sampling loops. That is, pictorially, as you remove noise, you add noise back. And then you remove noise again, you add noise back. You repeat this back and forth oscillating noise removal and adding back before you will actually move toward the next denoising schedule step. This way, you can actually achieve much better steering. For example, now the policy can be steered effectively to generate a particular motion trajectory that's indicated by the user preferences without actually causing the trajectory to be incoherent.
I have a question.
Yes.
So for the diffusion policy, the base policy here, what is the kind of data distribution that you sort of collected for to sort of help you performing this steering? So does it cover like where the points will most likely be pointed to?
Yeah. So the diffusion policy during training has never seen this point input. That is the yeah. So this is why this is called Inference-Time policy customization. It has never been trained on interaction data. This is the completely additional information added at test time, at inference time, during the sampling procedure.
I see.
So yeah, that is. If you look at the pseudocode here, this diffusion policy is pre-trained. It's given to you. And then the alignment gradients is just added during the inference time, during sampling. Yeah.
So is it trained on just play data then in the environment?
Yeah, that's right. That's right.
Okay. Also, another quick question. The user interaction, you mentioned there's clicking and sketching. Is this on the image plane or is this in 3D space?
Yes. So those are on the image plane, and then you use some heuristic to map it to the 3D space.
Okay.
Okay, cool.
Wait, maybe just one last question. So like some paper, like recent paper with like VLA models, they try to just draw lines or sketch directly on the image plane, and they use a pre-trained diffusion policy or any kind of like low-level policies, and they show that it might sort of be able to steer the action towards the target based on the visual sketch that's just on the image. Like, do you try that before?
If I remember correctly, you're referring to RT trajectory or trace VLA. All those approaches, all those approaches requires fine tuning. If I remember the details correctly, yeah. So the approach we have here doesn't require you to actually fine tune your policy to do that. Yeah. So that's the major difference, I would say.
I see.
But the commonality is we agree with those papers that trajectory sketch is actually a really good intermediate representation for your task that people should exploit more in their work, either in the fine-tuning case or in the inference stage case. Yeah. Okay, cool. So now we've shown some qualitative examples. This stochastic sampling is performing better than guided diffusion. But you might ask, like, what is the underlying intuition why this might work better? Let's look at this toy example. Let's say your diffusion policy has learned this pre-trained distribution. It has multiple modes. Each mode is corresponding to a different skill or different task. If you do unconditional like diffusion sampling, as you see here, you will end up with samples coming from those modes. And if the user wants to control this process, let's say in this case using a point objective function shown here, you can generate alignment gradient and compose the two. If you do this guided diffusion, what you will realize is when this point objective is not perfectly aligned with the pre-trained distribution, you are effectively sampling from the sum of those two distributions, right? And then when the point objective is not perfectly aligned with any of the mode of the pre-trained distribution, you will introduce distribution shift because you're going to sample from a region that's slightly off the peak of the pre-trained distribution. What ideally you want to sample from is the product of those two distributions, so that even when the point objective is not perfectly aligned with any of the pre-trained distribution mode, the product of them will still be in distribution. And this is exactly what stochastic sampling is allowing you to achieve, is to allow the sampling process effectively finds the in-distribution mode that's closest to the point objective function. So you can perform this constraint optimization, that is minimize the distance to your user objective, minimize while subject to staying in distribution of your pre-trained policy. So this is why stochastic policy will perform better than guided diffusion. And then to give you some idea of how you can do this human-robot interaction in real time, if you focus on the scene camera view on the top right, you will see whenever the human activates steering by turning that red sphere into green, the robot behavior will change. For example, here, the steering allows the robot to pick up a different ball. And then as the robot will put this ball in the microwave, and then close the microwave door, the user will guide the robot to pick up the different ball. For example, as you will see very soon, here, steering activates, and then the robot will go to the door. And then you can see here, this is the case of distribution shift because the robot fails to pick up that ball. But the nice thing about this online correction is you can keep trying until the robot succeeds your task. You don't have to stop the robot and restart the policy from the beginning and try it again. You can just keep continuously providing correction feedback until the robot does your thing. Okay, a summary slide. This slide is a little bit busy, but let me parse it for you. Each data point is a different combination of a base policy and a different sampling strategy. I only covered guided diffusion and stochastic sampling here, but there are other sampling strategies we explore in the paper. The whole point is, if you want to keep the policy frozen, that is, you don't want to fine-tune the weights, as you increase alignment, as you improve the alignment by reducing your misalignment rate, you will inevitably introduce failures. That is, there's this tension between alignment and staying in distribution if you want to impose the interaction at inference time. And then the key takeaway is this particular combination of stochastic sampling coupled with diffusion policy gives the best trade-off between alignment and the success rate. Okay, so with that, I'm going to move to the next section unless you guys have questions. Okay, so far I talked about how do we allow users to indicate spatial preferences, right? For example, do you prefer the robot to help you pick up the left ball or the right ball? Let's say the robot is capable of generating long multi-step skills such that it's possible to perform a sequence of skills such as pick up left ball, place ball in sync, and pick up right ball. And there are other sequences that are feasible, valid into the future. How can we allow users to steer the policy to perform this longer multi-step sequence? As you probably guess, a point input is no longer sufficient to capture the temporal structure of multi-step tasks. So for the next section, we're going to explore using a symbolic multi-step plan to indicate preferences. And then how can we use that to help the robot to stick to a particular plan? So the second part of the talk, I will talk about task and motion imitation, which is a framework that allows us to do motion imitation that will always satisfy a discrete task plan, even as the user customizes the motions. So this is a motivating example. Let's say this pre-trained policy is learned from the demonstration of reaching some marbles and scooping some marbles and transporting the marbles to put in the target ball. Right? It's multi-step. There's a temporal structure here for this demonstration. And then the success criteria for this task is to deposit at least a single red marble into the target ball. And during the policy execution, let's say the user wants to customize the motion by moving around. Here, for example, the user wants the robot to actually transfer marbles from this part of the state space. Notice after the interaction has stopped, the robot is still holding marbles. That is, it is still in the transporting mode. But policy execution from that particular mode can potentially lead to future mistakes. That is, the policy has carried out a different discrete plan, multi-step plan. The moment it drops the marbles, it's no longer in the transporting mode, it's back in the reaching mode. So this is the plan not intended by the user. So can we actually modify the pre-trained, the erroneous pre-trained policy's behavior by imposing this symbolic multi-step plan explicitly in the symbolic form to specify what are the legal mode transitions and what are the illegal mode transitions? Can we use this to change the behavior of the pre-trained policy? You might, for example, now condition on this additional multi-step plan given inference time, the robot will be able to change its behavior. And whenever it realizes it drops the marbles, it will go back and replan so that the user can feel free to customize the motions by pushing it around without worrying about the robot will carry out a different plan intended by the user. So you might ask how this could possibly work. The high-level idea this might work is this symbolic plan is defining a set of motion manifolds. For example, a reaching manifold, a scooping manifold, and a transporting manifold. But that is, we can partition the state space into these three intersecting motion manifolds where the mode boundary is encoding constraints. For example, the mode boundary for scooping is encoding the constraint that during scooping, the spoon must be in contact with the marbles. And then if we can recover this manifold task structure, we can force the motion generation from the imitation learning policy to live on this manifold and then proceed in this sequential fashion. And whenever the motion policy is detected being outside of the manifold, such as dropping marbles, we can bring it back so that we can ensure the task success. So this is the framework called task and motion imitation. And then let's look into some detail like how this can be possibly implemented. So the task we have at hand is, let's say this pretrained policy cannot generalize safely. From this part of the state space, its generalization will lead into dropping marbles and potentially a different task plan. Given this robot, the symbolic plan, the correct way of solving this task at inference time, and also a mechanism for users to monitor when the robot is making a mistake, we want to be able to use this inputs to change the behavior of the underlying policy without fine-tuning it. So this is the high-level goal we want to achieve. If you look at the motion policy learned by this pretrained policy projecting onto this 2D space, we can see this, for example, this orange dot is indicating the location of your target ball. And then these dashed boundaries are indicating the constraints on the gripper pose, for example, so that the spoon will remain level so that it won't drop the marbles. Or the blue trajectory are successful executions that take marbles to the target ball. And then the red trajectories are those motions that drop the marbles before reaching the ball, even though eventually they do reach the ball. And we would like to learn constraints so that it approximates the boundary of the mode, and then keep all of the motion stay inside on this manifold, so that all of the motion generation will carry marbles to the target ball. So how do we achieve this? Because the mode boundary is never given to us, the user only teaches robot motion demonstrations without labeling the constraints during the training stage, right? So we need to first recover the mode boundaries. One idea of recovering it is when the user is customizing the motion of your robot by physically moving around, the moment it causes some failure event, we can monitor that, and then that failure event must be living on the boundary. What you can then do is to find the separation, a cutting plane that separates the failure event and all of the previous in-mode states. If you have more and more interactions that cause more and more failures, you can get more and more, increasingly more cutting planes that together they will get a better and a better inner approximation of your mode. Here we assume the mode is convex, so you can perform this procedure. And then once we recover these cutting planes, we can treat them as collision objects that bound the motion flow inside, so that the user can feel free to interact with the system inside this constraint set to customize the motion without worrying about breaking the task. Here's an example. The moment the robot experiences the failure of dropping marbles, a failure event will be recorded, and then you can leverage using that to change the policy output so that the robot will learn to maintain a constraint and keep the marbles until it drops them in the target ball. Notice this process doesn't require you to change the weights of your policy. It only affects the policy output after the motion has been generated. So if you look at our method, which is DS plus modulation, modulation is using constraint to change the behavior of the policy. Dynamical system is one variant of a behavior cloning policy. Here, we're showing our method compared to the baseline methods. In the case of no interaction, that is rolling out this policy open loop, most of them perform a task relatively high success rate. The moment we introduce human interaction to customize motions, baseline methods such as behavior cloning will actually drop performance, especially as the user becomes more and more aggressive in terms of customizing the motion through nudging. The performance drop will become increasingly bigger. And then the method of making sure the robot performs the motion execution subject to a discrete multi-step plan allows us to maintain the same high task success rate, even under interaction at inference time.
I have
Okay,
a question.
sure.
Yeah, sorry. So do you like, based on what you did here, like do you also observe that for like large scale data, like positive large scale data domains, for example, like Pi and all these kind of large VLA models, where they are not always trained like perfect data, and there might be states that was previously accounted before, and then through that data process itself learns to recover to the previous steps, or is it just more of like, in this case, do you think this effect sort of applies more for like smaller data regimes for PCs?
Yeah. So this work was completed way before the VLA era. So back then we didn't have the VLA to experiment with. So a lot of the methodology works for definitely works for a small data regime. But to answer your question, whether this method works for large data regime, and that's the first question. The other question is whether it is necessary to still perform this as our model becomes more and more powerful, whether maybe those models have their self-corrected behavior in themselves already through learning from large scale data, right? So these two questions, let me tackle them one by one. The first question is, does our method, can our method work with VLAs or large models? The answer is absolutely yes, because the moment you cover these constraints, the modulation, in fact, comes from, is only influencing the model output at inference time. That is, it doesn't make any assumptions of what model you're using. The moment you have a model that generates actions, our method essentially figure out what component of those actions that is going to cause constraint violation, and then make those components 0, so that it preserves all of the motion components that will obey constraints. So that effectively this modulation strategy is a plug and play with any motion generation model. Okay, now to your second question, which is, do we see better and better recovery behaviors from large scale VLAs? So I do see some behaviors from the recent Pi model, but it's nowhere from being super robust to the level that's showing here. For example, if you look at the purple bar, the robustness is, we actually have a theoretical guarantee on this robustness. So those models is nowhere near the reactive behavior we are introducing through this explicit task and motion imitation method. But will that become better as we scale the data? Possibly. But I still think there is going to be a little bit performance gap when you are deploying these models 0 shot in a new environment. That gap will definitely shrink, but I think in the foreseeable near future, that gap won't go away 100%. So that's when I think our method can play a role to bridge that gap in cases where users really don't want to stop their process and then fine-tune the policy. They want a quick fix on the job. So that's where our method will shine. Yeah.
Thanks.
I hope that's not too long of a, yeah, sorry.
Sorry. So you mentioned that you were modifying the actions outputted by the policy. So I mean, I guess it's going to cause a distribution shift, since you're changing the state distribution induced by the policy. So does distribution shift cause an issue here where your policy is going to be wandering outside of the support of the expert data?
Yeah. So actually, if you look, do I have something here? So actually, because we're recovering the constraints, right? Like, you're essentially bounding your policy inside the distribution that it knows how to perform the task. And that's why.
dense coverage over this like polyhedra that's based on the constrained hyperplanes?
We actually, for this policy you're seeing here, we just use a single demonstration. And then, the generalization of that single demonstration comes from this particular imitation learning method called dynamical system. It has a way to generalize beyond that single demonstration. So it has actually we don't have dense coverage over this state space, but that particular imitation learning method has some generalization. But what that method doesn't have is this constraint satisfaction. That is, it doesn't generalize in a way that always stays inside a constraint set. That is why we need to sort of recover the constraint set explicitly and impose that. So now we'll be able to have generalization that's both safe inside the constraint set, and it will also reach the target. So that's, yeah, I hope that answers some of your question.
Awesome. Yeah. Thank you.
Yeah. Okay, cool. So for the last bit of this work, I really, because just now, I think that framework is nice, but it requires the user to monitor when the robot, monitor those failure events. What would be nice is to actually learn a classifier that can automatically do this job for you, so that a user doesn't have to pay attention to when the robot is failing and direct the robot to do something differently. What that amounts to is something called is to learn a classifier. That is, we want to learn a classifier given a robot state and an image observation of the scene. That classifier can tell you whether the robot is in this reaching mode, or this scooping mode, or this transporting mode. That is essentially, you want to learn a classifier that can partition the space into different manifolds, manifold structure. And I call this process like grounding. We're grounding continuous data such as motions and images into the discrete plan given by the symbolic task specification. So the way, the most straightforward way or naive way of learning this classifier is to ask humans to densely label each part of your demonstration, for example, which state or which mode it is in, right? But that can be a very daunting task. And then what we want to try is something, can we leverage the pre-trained policy's successful execution, and then maybe also add some perturbation to it, but to generate counterfactual outcomes, that is exploring when this pre-trained policy will fail, using this contrasting information and additionally the discrete symbolic plan that describes what makes the trajectory fail and then what makes the trajectory successful, using these as inputs to learn the classifier. So this is actually a very hard task. We essentially want to leverage very sparse labels of the execution outcomes to infer the dense manifold structure. Okay, so intuitively this could work in this fashion. Let's say you randomly initialize your classifier weights, right? Your classifier might propose during the early stage of your training, your classifier might propose to partition your space in these three intersecting manifolds. And then, according to the given symbolic plan, both trajectories should be successful, right? Because they all go through legal discrete transitions given by the symbolic plan. However, this prediction will be inconsistent with the ground truth label. That is, one of them should actually be a failure event. So maybe you want to incorporate this discrepancy into some loss term, and then do some gradient descent in the weight space of the classifier. Now your classifier might stumble upon a different way of partitioning the space. Again, according to the symbolic plan, both will be unsuccessful executions because both of them go through this invalid mode transition directly from reaching to transporting. So that, maybe this is not the correct way, this is not a great classifier, you do some gradient descent, and then eventually you might stumble upon this way of partitioning the space. And then according to the symbolic plan, you can actually predict one of the trajectories is successful and another trajectory is unsuccessful, consistent with the ground truth labels of those two trajectories. If you have lots of such positive and negative trajectory pairs, you can actually use this method to learn relatively smooth and sharp boundaries that recovers your mode structure of the task. An example of what could be learned is an image classifier And that tells you whenever the spoon is dropping marbles, as you see here, the Boolean vector corresponding to which mode it is in will switch, will change Boolean values the moment it drops marbles. So this you can learn quite sharp mode classification. And then this is an interesting core example that showcasing, this is just projecting the high dimensional mode structure onto 2D plane. So essentially for this task, the successful manipulation requires you go through mode 1, 2, 3, 4, 5 in this sequential order. And then with our method, you can actually recover the boundaries of these modes quite accurately. But what's interesting is if you remove the negative data, if you only use successful positive data, you won't actually be able to learn the sharp boundaries. You really need those negative data to know where to put the boundaries. And then lastly, if the symbolic plan is somehow wrong, then you might learn the rough shape correctly, but you will learn the wrong partition because that's intimately tied to the coupled with the symbolic plan. Okay, so to tie up this last two works, we're proposing a framework called task and motion imitation, where we want to allow the user to customize or steer the pre-trained policy subject to the task constraint given by the symbolic plan at inference time, and then achieve the capability, as you see here, of a robust task outcome under user interaction or steering during inference. And then this policy is quite robust. We actually have it on display at MIT Museum. So if you ever find yourself in Boston, we welcome you to actually go to the museum and try our robot demo. It's being on display 24/7 for the past 2 years. It's still working. And okay, to summarize what I've talked about so far, given a pre-trained policy that has learned multimodal behaviors, we want to control this process. One way to control it is to fine-tune it so that it will take online inputs, interaction input from users, right? This is one approach that many people are doing. What we're doing differently here is we don't want to change the policy yet. What you can do is find out ways to map user interaction to some cost function and use that to bias the sampling to achieve a particular behavior. And then lastly, you can also use this framework of task motion imitation to infer task constraints from user interactions and then use that to correct the policy behavior to improve the policy output under interaction. Okay, so where are we? Like, what's the big picture? Like, why am I doing what I just did? The goal is to bring robots to people's homes or factory floors so that people can use them. Right now, people are doing a lot of effort goes into pre-training, right? People train VLAs, vision language action models in lab environments, and then they want to deploy it. You will typically see a performance drop when you deploy these models in novel environments. But that's fine. People will then, in that new environments, do some data collection and then fine-tune the VLA and then get the performance back up. But even now, the fine-tuned version of the VLA has adapted to the visual statistic of your new environment, there still may be tasks that it will fail, right? In those cases, can we allow users on the job do some quick fixes? And that is the customization techniques I proposed that summarizes my past work. But there's a big limitation of this work because my past work assumes that we want to keep the policy frozen. That is, we don't want to change those policy anyways. And that really introduces this tension between misalignment and the failure. You cannot improve alignment without a cost, and your cost in this framework is the degraded performance. So a more fundamental way of allowing users to give users more knobs to tune the policy behavior is during the fine-tuning stage. That is, how can we train VLAs that are steerable, that are mindful of downstream interactions, so that when the language prompt fails to elicit the correct behavior, the user has other knobs to steer the policy. So more concretely, to learn this steerable VLA, that is, we want to learn a policy that's not autonomous, but it's really conditional on online interaction inputs in the form, for example, of key points that tell you what are the important objects to manipulate, or trajectories, right? These are intermediate representations that are very explicit and potentially less ambiguous than language to help ground the task. And then the user can use these intermediate representations to steer the policy, if the policy during training is already conditioned on these inputs. And then this is just something that's ongoing that I'm working on, is we're trying open VLA in our lab environment to pick up this tomato. And then you will see it generally does something in the right, it goes to the right direction, but then it just fails to actually pick up the tomato. If you can somehow turn these VLAs into a trajectory follower, now you can just draw a trajectory in the image space and then let the robot to follow the image trajectory. And maybe this is an effective knob to control the robot to finally reach the target and grasp it. Okay, so this is one line of work that I hope to explore. The other way we can make these policies easily tuned or steered is at a fine-tuning stage. That is, can we do fine-tuning without changing all the ways in this end-to-end system? Can we somehow localize part of the network that requires fixing? If we can do that, then we potentially don't need as much data as the other fine-tuning frameworks require to achieve fast adaptation. So consider this example I showed earlier. Let's say when the robot fails to perform this task, even though it's given a correct language instruction. Why do these policies make mistakes, right? Where does that mistakes arise from? So if we can do some policy interpretation, if we can sort of investigate the network a little bit, understand where do the policy make mistake, then we can actually do those localized fine-tuning. So one of my past work tries to explain policy mistakes by explicitly recovering the task structure and then use that to explain why a particular execution is a failure. What I want to explore next is, let's say, given an end-to-end big model, can we somehow visualize the activation of these neurons and then find which layers are doing the task of mapping language command to a task specification, and which layers are doing the task of mapping task specification to action prediction. And if, let's say, the errors happens from this first grounding process of mapping from language to task specification, for example, visualized by this attention map, let's say you give a language command, but the attention map shows the model is paying attention to the wrong region of the image space, then you can actually do activation steering on those neurons to suppress the activation and resulting in a changed behavior. And then you can further do fine-tuning on those layers to bake in the correction, to basically fine-tune these intermediate representations to get quick updates. So this is the second direction I'm interested in exploring. And then the second direction actually allows us to understand how these VLAs make decisions. And then especially if it somehow tells us part of the decision-making comes from this grounding, or some of the errors come from this grounding, we can tap into non-embodied data, right? So right now, a lot of these VLAs are trained on VQA data. Those VQA data might not be the best data to train your policy to make the connection between your language and the vision input for the use case of manipulation. If we can identify those grounding errors, what you can do is we can potentially leverage a lot of the manipulation videos or human manipulation videos without the robot embodiment. This kind of data is not useful for robot action prediction, but still useful to help us fix the grounding part. And this data is much more abundant than collecting motion trajectory through kinetic teaching or teleoperation. So I think this is the third direction I'm super interested in exploring, is how can we leverage non-embodied data that still get us a better VLA performance, so that we now only require fewer action labels to train the entire model. Okay, the overall idea I want to do these different directions is so that our end users who have the robots in their homes on their factory floors have easy ways of customizing the behavior of the robot so that they can get the robot to do the task they want the robot to do. And only when we make this process easy will we incentivize more and more users to use the robot. And then through that process, a lot of the corrective behavior, corrective feedback from users can get logged and then used to improve the robot behavior overnight when the user is not using the robot. So I see this as a cycle where the people use robots more and more, and then the robot becomes better and better in their capability in terms of assisting humans. And to achieve this goal is my research agenda, or my research goal is to achieve this paradigm, to realize it in the real world. Okay, with that, I thank you everyone for listening, tuning in, and I thank all my collaborators. And then I would like to open up to questions.
I have a question. Like, so for the third, so you mentioned like 3 things that you sort of wanted to do as future work. So like, is there any take on how you will do the third one? I'm not sure if you can go back to the slides.
Yeah, of course.
Yeah, this one, yes.
So, yeah. So for example, I think for a lot of the VQA data set, the data comes in the form of an image and then some, classification task or descriptive task that are not really reasoning about spatial components in the image space. So training this mapping from language to the image input may not give you representation useful for the downstream manipulation tasks that require spatial reasoning. So one way to get that done is, let's say, a lot of the videos in, for example, we have a lot of YouTube videos of user manipulating different objects, right? We can employ vision classifier to predict where the hand is going, like what object will be manipulated in the next frame, stuff like that. And those labels will be much denser in terms of spatial distribution, and it will give you more information about that are more suitable for potential downstream manipulation tasks. And you can use those labels to fine tune these layers. That is the early layers of your VLAs, so that training those parts of the model doesn't require action labels, like a real robot embodied action labels. So that's one.
So how does that differ from like VLA's code training process with like large scale image, internet scale data? To understand, I think what I'm trying to get into is like, are you talking about like semantics that's transfer from non-embodied data, or how do you sort of ground those non-embodied data to, as you put here, stability of VLA models?
Yeah. So I think maybe I didn't explain myself clearly, but I think a lot of the VLA training, the pre-training, they're using VQA tasks or tasks that are not necessarily directly related to manipulation tasks, right? So the hope is these layers will get semantic features, but not necessarily the spatial reasoning capability, like where things are, for example. What we want to do is generate special purpose data sets. For example, for if the model eventually wants to generate actions to manipulate objects, then the model really need to learn to pay attention to movable objects or manipulable parts of the objects. Right? Those are of much granular at a much granular level than a lot of the VQA tasks. So if we can label those through pre-trained vision models, and then we can basically use a lot of the human manipulation videos to generate those kind of special purpose tasks to teach the robot to recognize manipulable parts of the objects. That's one way. The other way is we can ask users to label constraints that must be satisfied during non-prehensile tasks, such as transporting things without spilling. And those constraints can be auxiliary tasks to complete, or we can make those into auxiliary loss as you are training the early layers of your VLA that fuse language instruction and image inputs. So all of these doesn't require embodied robot action data, right?
I see. So do you think that the current state of like language models or even like vision language model is able to provide those constraints that you just mentioned, which is if you are performing a task to transfer objects, what is some of the constraint you shouldn't spill? Because there is work that uses, VLMs or LLMs to sort of set constraints and do zero-shot manipulation. So
yeah, absolutely. So I think a lot of these models, they are implicitly doing that, right? Because they are trained on successful demonstrations. So those constraints are implicit in the successful demonstrations. They are the model output is going to obey these constraints statistically. But the issue here is when the model is not able to perform the task, and then the user wants to interfere, and then adding interaction or corrective feedback, that thing is going to actually break these implicit constraint satisfaction that the model will have, right? So we want to be able to allow the user to steer the policy to interfere in a way, but still somehow the model is still able to reason about the constraints. And this is an example I showed you earlier. As the user interferes with that scooping transporting task, the robot will end up in a state that's out of distribution, and the generation from that out of distribution state is unsafe. When we're deploying the VLAs, when the user is never in part of the loop, yes, those policies likely will be in distribution. The moment we start to have humans interacting with those policies, chances are the robot will land in those out of distribution states that it has never seen during training. And then how do you generalize from those states in a safe fashion requires this explicit reasoning of the constraints, which is not currently part of the pre-training of the VLAs. I hope that kind of answered your question.
Yeah, thanks.
In the second part of your future work, you were talking about adaptation of these models, these VLA. Are these methods different from what people have already done with LLMs in terms of adapting to new domains or new kinds of tasks?
Yeah, I think I get a lot of inspirations from LLM kind of literature. So I think I would first try those. Like I'm not trying to make any like algorithmic innovations yet. I think the first thing I want to try is to try those methods that work for LLM and see how it might fail in this motion generation framework, right? Like, for example, a lot of the guided diffusion methodology initially just comes from the guiding region-based diffusion model or other modality. The same methodology work great for region domain. That's because people cannot discern like those tiny out of distribution stuff in the image space. But that becomes much more aggravated when you want to execute a trajectory successful. And then that invites innovation, right? So because we need to make it work for the manipulation domain. So I assume what will happen is I'm going to try a lot of the methods that are well tested in the LM literature, apply it in this domain, and then something will break. And that's when we can make the innovation to somehow make it still work for our imitation learning or manipulation domain.
Do you imagine any, or can you think of any sort of specific challenges in manipulation that might be unique compared to language modeling?
Yeah. So one thing that's unique about language modeling is a lot of the tokens you're predicting. The language data is already in highly abstracted space, right? That is, each nearby tokens, they're not necessarily highly correlated. It's already the information density in the same number of tokens are really high. But if you look at motion trajectories, they're not really in a very highly abstracted space, right? Nearby states in the manipulation trajectory are highly correlated. So for the same amount of manipulation trajectory, the information density is a lot lower. So I think that will probably introduce some issues, which is why actually in the second part of my work, I tried to extract this task representation in the form of motion manifolds, right? That is exactly, I want to figure out what's the best way of representing these demonstrations in a much more abstract way. So I think that's a major difference between motion prediction and next token prediction in the LM domain. Yeah.
Right, in the spirit of time, I think we should end. We're also holding off other people.
Yes. Thank you so much. Thank you, Felix.
Thank you everyone for taking the time.
Thank you.
Thank you, Felix. Have a good day of
Thank you.
interviews today.
Yeah, thank you.